Hello and welcome to this research highlight video. My name is Ernesto Perea and I am a research assistant at the University of New Mexico at the Center for Water and the Environment. Today I'm going to show you a little highlight of the recent work I've been completing at the university. So my focus of work is the interaction between energy and the environment. And we are focusing on reactions in the microannulus of a wellbore system with produced water brine from the Permian Basin. So how does energy and the environment interact? In New Mexico, we have become one of the top 10 energy producers in the US for oil and gas. This includes the implementation of new drilling techniques and production techniques like horizontal drilling, hydrofracking, and enhanced oil recovery. This growth has also led to the growth in the water use quantity from this area. The water that is used by the oil and gas industry has been deemed produced water and is largely removed from the water cycle after use because of its poor water quality. So a little overview of these wellbores. They're quite deep, up to 2 kilometers deep, and they are intended to isolate these wellbore fluids from the environment. And these wellbore fluids include greenhouse gases. So what are these wells made of? They're comprised of cement and a steel casing. And the wellbore fluids flow through the steel tube, and the cement is meant to surround the steel to the formation, creating this barrier or isolation from the environment. So there's 3 main mechanisms that cause the failure of this isolation from the environment. They are physical, mechanical, and chemical. We will be focusing on the mechanical and chemical mechanisms in my work. So what is the knowledge gap that we're trying to fill here? There's a lack of knowledge of what happens to a micro steel casing, and that causes debonding from the cement. So the objective of my work is to determine the effects of this produced water on the wellbore materials and how does that change the integrity. So I am hypothesizing that there will be a formation of precipitation products and reduction oxidation products that happen in this annular space, and then that this precipitation in the annular space will cause a decrease in the permeability. So my experimental approach is cut into 2 phases, where one phase is going to be with a lab quality brine, and then the second phase is a field sample brine. So some ways that we're going to achieve these techniques is using changes in aqueous concentration. We're going to use visual and electron imaging to determine any visible precipitates. We're going to measure the permeability changes over the life of the reactor and try and quantify some of the changes in the solid surface. So initial look at the water quality results. We've created a lab quality brine that closely matches our field sample. We are tracking the pH over the reaction times, and we are seeing that cement causes the pH to go up, while steel-only reactions cause the pH to decrease slightly. So just a quick visual inspection of some of these samples that we've created. We can see that there is an increase in visible precipitate over the time of reaction, and this was also seen in the control samples of cement and steel. So we sealed these samples after reaction using an epoxy and then sliced them using a diamond blade and polished them up so that we could take a look at this interface more closely. As you can see on the top left and bottom right, that we can get a really good look at this microannulus just using a digital microscope. But to quantify these reaction products, we're going to use EPMA, which is electron probe microanalyzer, and we can take a much closer look at this microannulus and try and quantify some of these elements. So we can see that steel is comprised mostly of iron, and the cement is a mix of calcium, silica, and this was also completed for the steel control samples, where steel is still mostly iron, and then no elemental composition for the Teflon. So we looked at the cement control samples, and we also saw that calcium and silica were dominant in the cement. So looking at the reacted interface, we can see that there is a formation of precipitates in this microannular space. At 24 hours, we found that there was a magnesium-dominated precipitate, and at 240 hours, the precipitate that we found was dominated by calcium. And then we looked at these same samples using XRD to try and quantify the phases, and we found that there was an increase in amorphous phase while decrease in the Portlandite and Hatterite phases. Then we completed a duplicate reactor when we didn't seal them, and then measured the permeability after the reaction, and we did find that the permeability is decreasing over time. And this can be good because this can show that wells will decrease the emissions of greenhouse gases over the life of the well if there is a mechanical failure followed by the influence of this produced water brine. So thank you for your time. Please check out the CWE website, and thank you.